parallel universes real? It's a question that has fascinated scientists, philosophers, and storytellers for decades. The idea that there might be other versions of reality, perhaps infinitely many, where events unfold differently is both mind-boggling and captivating. In this video, we'll explore the scientific theories, the evidence, and the big questions that arise from the possibility of parallel universes. Before diving into the theories, let's define what we mean by a parallel universe. In simple terms, it's an alternative reality that exists separately from our own universe. These alternate realities could be similar to ours, with only minor differences, or they could be completely alien, with different physical laws and structures. The concept of parallel universes isn't just science fiction. It's grounded in real scientific theories like the multiverse theory. The multiverse suggests that our universe is just one of many, perhaps an infinite number of universes, each with its own set of conditions. But where do these ideas come from, and how seriously do scientists take them? One of the most popular theories supporting the existence of parallel universes is the many worlds interpretation of quantum mechanics. This theory suggests that every possible outcome of a quantum event actually happens in a different universe. Imagine a world where you made the opposite decision at a key moment in your life. According to this theory, that world could exist in another universe. Quantum mechanics, the science of the very small, plays a huge role in the discussion of parallel universes. It describes how particles behave at the smallest scales and suggests that reality is far more complex than it appears. In fact, the equations of quantum mechanics allow for the possibility of multiple outcomes happening simultaneously, which opens the door to the existence of parallel universes. Cosmology also offers a potential path to parallel universes through the theory of cosmic inflation. This theory explains the rapid expansion of our universe just after the Big Bang, and it implies that other universes could have formed during this process, each one expanding and evolving on its own. These are often referred to as bubble universes, each with its own unique conditions. Then there's string theory, which offers another perspective on parallel universes. String theory suggests that the fundamental building blocks of the universe are not particles, but tiny vibrating strings. These strings may exist in multiple dimensions, and some scientists believe that this framework could support the existence of multiple parallel universes. But where's the evidence? Are there any signs that parallel universes could actually exist? Some scientists point to anomalies in the cosmic microwave background radiation, the afterglow of the Big Bang, as potential hints. Others are looking at gravitational waves, which might carry clues about collisions between our universe and others. Still, it's important to note that the idea of parallel universes faces significant challenges. Many scientists argue that, until we have direct evidence, these ideas remain speculative. The mathematics might support the existence of parallel universes, but proving their existence is another matter entirely. So, why are we so fascinated by the idea of parallel universes? Beyond the scientific intrigue, the concept resonates with our curiosity about alternate realities and the possibilities of what could have been. It's no wonder that parallel universes have become such a popular theme in books, movies, and TV shows, capturing our imagination and fueling endless speculation. The multiverse concept suggests that our universe may not be the only one. Instead, it could be part of a vast collection of universes, each with its own unique properties. These universes might exist in different dimensions, far beyond what we can observe. In this framework, the term multiverse refers to the entirety of these different universes, existing alongside one another. Some may follow similar laws of physics to ours, while others might operate under entirely different principles. The possibilities within the multiverse are thought to be endless. One way to think about the multiverse is to imagine each universe as a bubble. These bubbles could be floating in a vast, higher dimensional space, never touching or occasionally interacting with one another. Each bubble represents a universe with its own distinct beginning and evolution. The multiverse concept extends from theories of cosmic inflation, which propose that the rapid expansion of space after the Big Bang might have created separate regions of space-time. In each region, different physical conditions might prevail, leading to the formation of multiple universes. Our universe is just one of those regions. One of the intriguing aspects of the multiverse theory is that it allows for the existence of universes where every possible outcome of events plays out. For example, in one universe, a particular event might have one outcome, while in another, the same event could unfold differently. This leads to the idea that every decision we make could create a new universe. These alternate realities, or parallel universes, could be nearly identical to our own, or they could be drastically different. Perhaps in another universe, gravity is weaker, or life as we know it never evolved. Each possibility reflects a different set of initial conditions that shape that particular universe. Multiverse theories also vary in scale. Some propose just a few alternate universes, while others suggest an infinite number, with every conceivable variation of physics and reality. The idea of an infinite multiverse raises profound questions about the nature of existence and what it means to live in one specific universe among countless others. One of the key elements driving the multiverse concept is quantum mechanics. In the quantum world, particles can exist in multiple states at once. When observed, they collapse into one state. But the theory suggests that other states could persist in separate universes. This is where the idea of multiple realities arises. Another major influence on the multiverse idea is string theory. This theory proposes that the fundamental particles in our universe are actually tiny, vibrating strings of energy. In some versions of string theory, these strings could vibrate in different ways in different universes, giving rise to completely different physical properties. While the multiverse concept is compelling, it's also controversial. One of the main challenges is that it's nearly impossible to test or observe other universes. If they exist outside our observable space, we may never be able to gather direct evidence to confirm or deny their existence. Despite these challenges, the multiverse theory has gained traction because it helps to explain some of the strange and unexplained phenomena in our universe. For example, it could offer answers to why the physical constants of our universe are so finely tuned to support life. In a multiverse, there could be countless other universes with different constants where life is impossible. Ultimately, the multiverse theory stretches the boundaries of our understanding of reality. It opens up possibilities that challenge the way we think about existence, the nature of time, and even our place in the cosmos. However, it also raises more questions than answers, pushing the limits of both science and imagination. Several key physicists have played major roles in developing the idea of multiverses. One of the most prominent is Hugh Everett, who proposed the many worlds interpretation of quantum mechanics. His work suggested that all possible outcomes of quantum events happen in different branching universes. Max Tegmark is another influential figure in the field. He developed a classification system for different types of multiverses, organizing them into 4 levels. Tegmark's work has been crucial in bringing scientific structure to what can seem like a highly speculative concept. Stephen Hawking also contributed to the discussion of parallel universes. His work on black holes and quantum gravity suggested that other universes might emerge from the singularities within black holes. Hawking's research opened up new ways of thinking about how universes could be connected. Alan Guth is well known for his work on cosmic inflation, which is closely linked to the multiverse concept. Guth's theory of eternal inflation suggests that our universe is one of many bubbles, each with its own unique properties. His contributions have laid the groundwork for understanding how multiple universes might form. Another key physicist is Andre Linde, who expanded on Guth's work with his theory of chaotic inflation. Linde proposed that universes are continuously being created, with each one evolving according to its own set of physical laws. His ideas have helped to shape the modern understanding of the multiverse. David Deutsch is a leading figure in the study of quantum mechanics and the multiverse. His research into quantum computing supports the many worlds interpretation, suggesting that parallel universes could be directly tied to how quantum computers function. Deutsch's work brings together cutting-edge technology and theoretical physics. Physicist Brian Greene is well known for his work on string theory and the multiverse. Greene has popularized the idea that multiple dimensions exist, and that these extra dimensions could give rise to different universes. His books and lectures have helped make complex ideas about the multiverse accessible to a wider audience. Leonard Susskind, one of the founders of string theory, has also made important contributions to the multiverse debate. Suskind's work on the landscape of string theory suggests that there could be a vast number of possible universes, each with its own version of physics. His ideas support the notion of a diverse and complex multiverse. Roger Penrose, although skeptical of certain multiverse theories, has influenced the conversation through his work on cosmology and the structure of the universe. Penrose's ideas about cyclic universes propose a model where the universe goes through endless cycles of birth and rebirth, hinting at a different kind of multiverse. Paul Steinhardt, known for his criticism of eternal inflation, has offered alternative explanations for the universe's origins. Despite his disagreements with the multiverse concept, his work has been pivotal in shaping the ongoing scientific debate. His contributions provide valuable counterpoints to the more widely accepted theories. Alexander Vilenkin has also been a major figure in the discussion of multiverses. Vilenkin's work suggests that if space is infinite, it's inevitable that universes like ours will form repeatedly. His ideas have been influential in linking the concept of infinity with the possibility of multiple universes. Lastly, Michio Kaku has been instrumental in popularizing multiverse theory. Through his books and media appearances, Kaku has brought the idea of parallel universes into mainstream discussions. His ability to simplify complex scientific concepts has inspired a broader interest in the possibilities of the multiverse. The concept of the multiverse fits into current physics models by extending ideas already present in quantum mechanics and cosmology. In quantum mechanics, the many worlds interpretation offers a natural explanation for the probabilities we see at the smallest scales. This interpretation suggests that all possible outcomes happen in different universes, each as real as our own. Cosmology also provides a framework for the multiverse through the theory of cosmic inflation. Inflation explains how space expanded rapidly after the Big Bang, and some versions of this theory suggest that inflation never stopped. As inflation continues in different regions, new universes can form, each with its own distinct properties. String theory, which seeks to unify gravity with the other fundamental forces, also accommodates the idea of multiple universes. In this theory, there are extra dimensions beyond the three we experience. These extra dimensions could be home to other universes, each shaped by different fundamental laws. The landscape of string theory offers a mathematical model for how different universes might exist. It suggests that there are many possible ways for a universe to be configured, depending on the shapes of these extra dimensions. This gives rise to a huge number of possible universes, each with its own unique physical properties. Another area where the multiverse fits into physics is through the concept of eternal inflation. In this model, inflation creates pockets of space that stop inflating and become individual universes. Our universe could be just one of countless others formed in this way, each isolated in its own region of space. In the realm of black holes, the multiverse fits into physics through theories suggesting that each black hole could give birth to a new universe. This idea builds on the connection between general relativity and quantum mechanics, proposing that black hole singularities might lead to the creation of new space-time regions. These new regions could evolve into entirely separate universes. Quantum field theory, which underpins much of modern physics, also provides a foundation for multiverse ideas. In this theory, fields permeate all of space, and small fluctuations in these fields could potentially give rise to different universes. This connects the idea of parallel universes directly to the laws governing particles and forces. Another way the multiverse fits into current models is through the fine-tuning problem in cosmology. Our universe's physical constants are precisely set to allow life, which seems improbable. In a multiverse, this fine-tuning could be explained as one outcome among many, with most universes being unsuitable for life. The idea of parallel universes also arises in discussions of dark energy and dark matter. These mysterious substances make up most of the universe's energy and mass, yet remain poorly understood. Some theories suggest that variations in dark energy or dark matter could lead to the formation of other universes with different structures. Multiverse models also challenge the limits of observational cosmology. In our current models, we can only observe a portion of the universe, known as the observable universe. If other universes exist, they would lie beyond what we can directly see, meaning that the multiverse fits into the framework of what is scientifically plausible, even if it's unobservable. Physicists have also explored how the multiverse might be tested, even indirectly. Though we can't directly observe other universes, some theories suggest we might find traces of their existence in cosmic background radiation or gravitational waves. These possibilities push the boundaries of what we can test, but fit within the predictive nature of modern physics. Ultimately, the multiverse fits into current models by extending existing concepts in new directions. Whether through quantum mechanics, cosmology, or string theory, the multiverse offers a way to explain some of the biggest questions in physics, while still working within the frameworks already developed by scientists. Quantum mechanics is the branch of physics that deals with the behavior of particles on the smallest scales, like atoms and subatomic particles. Unlike classical physics, which predicts definite outcomes, quantum mechanics operates on probabilities. Particles exist in a superposition of states, meaning they can be in multiple states at once until they are observed. One of the central ideas in quantum mechanics is the wave-particle duality. Particles, like electrons and photons, exhibit both wave-like and particle-like properties, depending on how they are measured. This duality challenges the traditional view of particles as solid, defined objects. The Heisenberg uncertainty principle is another key concept in quantum mechanics. It states that you cannot know both the exact position and momentum of a particle at the same time. The more precisely you measure one, the less precisely you can measure the other. In quantum mechanics, particles are described by a wave function, which is a mathematical expression that represents all possible states of the particle. The wave function evolves according to the Schrödinger equation, which determines how a quantum system changes over time. Until a measurement is made, the particle's state remains in a superposition. Measurement plays a critical role in quantum mechanics. When a particle is measured, its wave function collapses and the particle assumes a definite state. Before this collapse, the particle doesn't exist in any one state, but rather in all possible states simultaneously. Entanglement is another strange and fascinating feature of quantum mechanics. When particles become entangled, the state of one particle is instantaneously connected to the state of another, even if they are separated by vast distances. This connection remains no matter how far apart the particles are, leading to what Einstein famously called spooky action at a distance. Quantum tunneling is the phenomenon where particles pass through barriers that, according to classical physics, they shouldn't be able to cross. This happens because of the probabilistic nature of quantum mechanics. There's always a small chance that a particle can tunnel through a barrier, no matter how strong. Quantum mechanics also introduces the idea of quantization, where certain physical properties, like energy, can only take on specific, discrete values. This is different from classical physics, where such quantities can vary continuously. These discrete energy levels are key to understanding how atoms and molecules behave. The superposition principle, which allows particles to be in multiple states simultaneously, leads to some of the most mind-bending consequences of quantum theory. Schrödinger's cat, a famous thought experiment, illustrates this concept by imagining a cat that is both alive and dead until observed, representing how quantum systems behave on a macroscopic scale. The probabilistic nature of quantum mechanics means that the outcomes of experiments can only be predicted in terms of likelihoods, not certainties. This fundamentally challenges the deterministic view of the universe held by classical physics, introducing a new way of thinking about reality. Despite its counterintuitive nature, quantum mechanics has been confirmed by countless experiments and is one of the most successful theories in physics. It underpins much of modern technology, from semiconductors to lasers, and continues to push the boundaries of what we know about the universe. At its core, quantum mechanics is a theory of possibilities and uncertainties, where particles do not follow the clear, predictable paths we might expect. Instead, they exist in a realm of probabilities, where reality only becomes definite when we observe it. The many worlds interpretation, or MWI, is one of the most fascinating ideas to come from quantum mechanics. It suggests that every time a quantum event occurs, the universe splits into multiple parallel universes. In each of these universes, a different outcome of that event plays out. In contrast to other interpretations, MWI avoids the idea of wave function collapse. Instead of collapsing into one state, the wave function continues to evolve, branching into different realities for every possible outcome. All these realities exist simultaneously, but we only experience one of them. MWI was first proposed by physicist Hugh Everett in 1957. He developed the theory as a way to resolve the paradoxes of quantum mechanics without the need for a special observer to collapse the wave function. In Everett's view, the universe is constantly splitting into different versions of itself. In this interpretation, every decision or event, big or small, creates a new branch of reality. For example, if you flip a coin, there's a universe where it lands heads and another where it lands tails. These universes exist in parallel, though we're only aware of the one we experience directly. One of the most intriguing aspects of MWI is that it applies universally, not just to quantum particles. The same principle that causes a particle to split into multiple states applies to everything in the universe. This means that every action we take could result in the creation of countless new realities. MWI also offers a new perspective on probability. Instead of saying there's a 50% chance of one outcome or another, the many worlds interpretation says both outcomes occur, just in different universes. The idea of chance becomes the experience of living in one specific branch of reality. Though MWI eliminates the need for wave function collapse, it introduces the concept of branching universes. Each time a quantum event occurs, reality splits, leading to an ever-growing number of parallel universes. These universes don't interact with each other, but they all stem from the same original state. The interpretation has been controversial, partly because it suggests a nearly infinite number of universes, most of which we can never observe. Critics argue that without a way to detect or interact with these other worlds, MWI may be impossible to prove or disprove, but it remains an elegant solution to quantum puzzles. MWI challenges our everyday understanding of reality. It suggests that every possible outcome, every alternative version of events, is just as real as the one we're living in now. This forces us to rethink our place in the universe and the nature of existence itself. Supporters of MWI appreciate that it doesn't require the introduction of any new physics. It sticks strictly to the principles of quantum mechanics, avoiding additional mechanisms like wave function collapse or hidden variables. For some, this simplicity is its greatest strength. While it's difficult to test directly, MWI has been embraced by some physicists as a compelling explanation for quantum phenomena. Its implications stretch far beyond the laboratory, touching on questions about free will, consciousness, and the very fabric of reality. The many worlds interpretation continues to inspire debate and curiosity. Whether or not we can ever confirm its predictions, the idea that countless versions of ourselves may exist in parallel universes is a profound and thought-provoking concept. Hugh Everett's contribution to the many worlds interpretation was groundbreaking, as he was the first to propose that quantum mechanics didn't require the collapse of the wave function. He challenged the dominant Copenhagen interpretation, suggesting that instead of collapsing, the universe splits into different branches for each possible outcome. His idea was that all outcomes happen, but in separate, parallel universes. Everett's doctoral thesis in 1957 laid the foundation for what would become known as the many worlds interpretation. In his work, he introduced the idea that every quantum event leads to a branching of reality. This was a bold departure from the idea that observation forces a single outcome. One of his key insights was that the observer doesn't cause the wave function to collapse. Instead, the observer becomes part of the system, experiencing only one outcome, while other versions of the observer exist in alternate universes. This eliminated the need for a special role of consciousness in quantum mechanics. Everett's work faced resistance when it was first published. Many physicists, including Niels Bohr, dismissed his theory, as the Copenhagen interpretation was the dominant view at the time. Despite this, Everett's ideas planted the seeds for future discussions on the nature of reality and quantum mechanics. One of the reasons Everett's contribution is so important is that it provides a deterministic view of quantum mechanics. In his theory, the evolution of the universe is governed by predictable laws, even though we only experience one branch of the multiverse. This contrasts with the inherent randomness of other interpretations. Everett's theory also laid the groundwork for thinking about quantum mechanics in a more universal context. By proposing that the wave function applies to the entire universe, he suggested that the laws of quantum mechanics hold at every scale, not just the microscopic. This was a significant leap forward in how physicists thought about quantum systems. Though Everett's work wasn't immediately embraced, it gained traction over time, especially among physicists looking for alternatives to the Copenhagen interpretation. His ideas have influenced a range of fields, from quantum computing to cosmology, showing the wide-reaching impact of his interpretation. Everett's legacy goes beyond just the many worlds interpretation. His work introduced new ways of thinking about the relationship between the observer and the system being observed. By removing the need for observation to define reality, he opened the door to a broader understanding of quantum processes. Despite facing skepticism in his lifetime, Everett remained confident in his theory. He believed that his approach offered a more complete explanation of quantum mechanics, free from the paradoxes that other interpretations seem to introduce. His persistence helped ensure that the many worlds interpretation wouldn't be forgotten. Today, Everett's contribution is recognized as one of the most important in the history of quantum mechanics. While his theory still sparks debate, it has inspired generations of physicists to explore new ideas about the structure of reality. His work continues to be a focal point in discussions of quantum theory. Everett's influence can also be seen in popular culture, as the idea of parallel universes has captured the imagination of writers, filmmakers, and audiences. While he may not have lived to see the full impact of his ideas, Everett's work has left a lasting mark on both science and the broader understanding of reality. Hugh Everett's many worlds interpretation remains one of the most intriguing and debated theories in physics. His bold approach to quantum mechanics continues to inspire, challenge, and shape how we think about the universe and our place within it. Schrödinger's cat is one of the most famous thought experiments in quantum mechanics. It was designed by physicist Erwin Schrödinger to illustrate the paradoxes that arise from the idea of superposition. In this experiment, a cat is placed inside a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. The setup is simple. If the Geiger counter detects the decay of the radioactive atom, the vial breaks, releasing the poison and killing the cat. If the atom doesn't decay, the cat remains alive. According to quantum mechanics, until we open the box and observe the outcome, the atom is in a superposition of decayed and undecayed states. This means that, in quantum terms, the cat is simultaneously both alive and dead. It's only when an observer looks inside the box that the cat's state becomes definite, either alive or dead. This highlights the strange nature of quantum superposition, where particles can exist in multiple states at once. Schrödinger's thought experiment was meant to demonstrate the absurdity of applying quantum mechanics to everyday objects. While the superposition of particles makes sense at the subatomic level, applying the same concept to a living creature like a cat leads to seemingly impossible scenarios. The cat being both alive and dead at the same time illustrates the central issue of quantum measurement. In the Copenhagen interpretation, the act of observing forces the system to choose one outcome. But until that observation happens, all possibilities coexist in superposition. Schrödinger's cat also raises questions about the role of the observer in quantum mechanics. Does reality only become definite when we observe it? Or is it possible that, like the cat, everything exists in a superposition of possibilities until we take a measurement? The many worlds interpretation offers a different explanation for the thought experiment. According to this interpretation, when the box is opened, the universe splits into two branches. One where the cat is alive, and one where the cat is dead. Both outcomes are real, but they occur in separate, parallel universes. In this version, the cat is never truly in a superposition of alive and dead. Instead, both realities exist, but we can only experience one. The other outcome happens in a different universe, and the cat's fate depends on which branch of the multiverse we are observing. Schrödinger's cat has become a symbol of the strange and counterintuitive nature of quantum mechanics. It forces us to confront the fact that the world behaves very differently at the quantum level than it does at the level of our everyday experience. It's a reminder that our intuition about how things work doesn't always apply in the realm of quantum physics. The experiment also highlights the tension between the deterministic nature of classical physics and the probabilistic nature of quantum mechanics. In classical physics, the cat is either alive or dead, regardless of whether we observe it. But in quantum mechanics, the outcome isn't determined until we look. Schrödinger's cat continues to be a powerful tool for illustrating the mysteries of quantum theory. It captures the complexities of superposition, measurement, and the role of the observer in determining reality. Despite being a thought experiment, it remains one of the most talked about concepts in physics. Although it was originally intended as a critique of quantum theory, Schrödinger's cat has helped shape discussions about the nature of reality. It challenges us to think deeply about the implications of quantum mechanics and what it means for our understanding of the universe. Cosmic inflation is a theory that explains the rapid expansion of the universe in its earliest moments. According to this idea, right after the Big Bang, the universe expanded exponentially in a fraction of a second. This incredibly fast expansion stretched space itself, smoothing out the universe and solving several key problems in cosmology. One of the issues that inflation addresses is the horizon problem. Without inflation, regions of the universe would be too far apart to have ever interacted. Yet we see that the universe appears uniform in all directions. Inflation solves this by suggesting that the entire observable universe was once a much smaller, connected region before expanding. Another problem it resolves is the flatness problem. The universe seems to have just the right density to be flat, which is highly improbable without an explanation. Inflation predicts that rapid expansion would flatten the geometry of space, much like inflating a balloon smooths out any wrinkles on its surface. Inflation also helps explain the distribution of matter in the universe. During inflation, tiny quantum fluctuations were stretched across vast distances. These fluctuations eventually became the seeds for galaxies, stars, and planets, as gravity pulled matter together in certain regions. The theory was first proposed by physicist Alan Guth in 1980. He realized that inflation could not only explain these cosmic puzzles, but also align with the known laws of physics. His proposal was a major breakthrough in our understanding of the early universe. Inflation suggests that the universe expanded faster than the speed of light during this brief period. While this might sound impossible, it's important to note that this doesn't violate the laws of physics, because space itself can expand without any object moving faster than light. Once inflation ended, the universe continued to expand, but at a much slower rate. The energy from inflation was converted into particles and radiation, creating the hot, dense state that we recognize as the Big Bang. This transition is what set the stage for the formation of atoms, stars, and galaxies. One of the most compelling pieces of evidence for inflation is the cosmic microwave background radiation, or CMB. The CMB is the faint afterglow of the Big Bang, and its uniformity across the sky supports the idea that the universe underwent a rapid inflationary expansion. Tiny variations in the CMB also match the predictions made by inflation. Inflation also predicts the existence of a multiverse. The process of inflation may have occurred in different regions of space at different rates, creating separate bubble universes. Each of these universes could have different physical properties, leading to the idea of a vast multiverse where anything is possible. The theory continues to be refined as scientists develop more precise models of how inflation worked. While the basic concept remains the same, there are several versions of inflation theory, each trying to account for new observations and evidence. Despite its successes, cosmic inflation is still a theory, and scientists continue to test its predictions. Ongoing research into gravitational waves, dark matter, and dark energy may provide further insights into the inflationary period and help confirm or refine the theory. Cosmic inflation remains one of the most important ideas in modern cosmology, offering a compelling explanation for how the universe began and why it looks the way it does today. It connects the smallest scales of quantum mechanics with the vastness of the cosmos, shaping our understanding of the universe's earliest moments. The concept of cosmic inflation doesn't just explain the early expansion of our universe. It also introduces the possibility of a multiverse. During inflation, space expanded rapidly, but inflation might not have occurred uniformly everywhere. In some regions, inflation could have continued indefinitely, creating new, separate universes. These different regions where inflation ends become isolated from each other, forming what we call bubble universes. Each bubble is a separate universe with its own distinct properties. Our universe would be just one of countless bubbles that formed as inflation slowed down in certain areas. What's interesting is that these bubble universes are likely to have different physical constants and laws of physics. Since inflation might have ended in different ways across different regions, the conditions in each universe could vary significantly. Some universes might support life, while others might be completely inhospitable. In this framework, inflation acts like a generator of universes. As inflation continues in some regions, more bubbles form, each becoming its own universe. This never-ending process suggests that the multiverse is constantly expanding and creating new realities. One of the key features of this idea is eternal inflation. While inflation ended in our universe, it could still be ongoing in other parts of the multiverse. This means that universes are constantly being born, even as we speak, from regions of space where inflation continues. Each of these universes is causally disconnected from the others, meaning they can't interact with one another. The space between them expands faster than the speed of light, keeping them forever separate. This makes it impossible to travel between universes, even if they coexist within the same overarching multiverse. In this view, the multiverse is a natural consequence of the inflationary model. If inflation happened, and if the universe is infinite, then it's almost inevitable that multiple universes would have formed. This takes the idea of a single universe and stretches it to a much grander scale. The randomness of inflation also plays a role in this. Quantum fluctuations during inflation cause small variations in how it unfolds across different regions. These variations determine the fate of each bubble universe, resulting in an endless array of universes with different outcomes. This multiverse concept fits well with the idea of quantum mechanics, where every possible outcome can happen in parallel. Inflation provides a physical mechanism for these possibilities to manifest, creating a reality where every version of the universe exists somewhere. If the multiverse exists, it could also help explain why our universe seems so fine-tuned for life. In a multiverse with infinite possibilities, some universes would naturally have the right conditions for life, while most would not. We just happen to live in one of the few universes where everything lines up perfectly. The concept of a multiverse challenges our understanding of reality. If inflation leads to the creation of endless universes, then our universe is just a small part of a much larger, more complex structure. This shifts the focus from understanding one universe to trying to comprehend the vastness of an entire multiverse. Inflation, once seen as a solution to problems in cosmology, has opened the door to the idea that our universe is just one of many. The possibility that there are countless other universes, each with its own history and laws, transforms the way we think about our place in the cosmos. Alan Guth is the physicist who first proposed the idea of cosmic inflation, a breakthrough that transformed our understanding of the early universe. In 1980, Guth introduced inflation to solve several major problems in cosmology, like the horizon and flatness problems. His theory suggested that the universe underwent a period of rapid expansion just fractions of a second after the Big Bang. Before Guth's work, there were gaps in the Big Bang theory that couldn't be explained by standard models of expansion. The universe appeared too uniform and too flat, which seemed highly improbable without a mechanism to explain it. Guth realized that a period of exponential expansion could account for these observations, leading to the concept of inflation. Guth's idea was that inflation stretched the early universe so quickly that any initial irregularities were smoothed out. This would explain why the universe appears the same in every direction, as inflation would have expanded small, connected regions into what we now observe as the entire cosmos. It was a radical departure from earlier thinking, but it fit the data remarkably well. One of Guth's key insights was that inflation could also explain why the universe is flat. Rapid expansion would drive the curvature of space to nearly zero, much like how the surface of a balloon appears flatter as it inflates. This flatness was something cosmologists struggled to explain before Guth's theory. His work also suggested that inflation wasn't just a one-time event. The energy driving inflation could persist in different regions of space, meaning some parts of the universe could continue to inflate while others stopped. This insight laid the groundwork for the idea of eternal inflation, and by extension, the multiverse. While Guth's original model had some issues, such as predicting an end state that didn't align with known physics, it was refined by others in the years that followed. Andre Linde's work on chaotic inflation, for example, built on Guth's ideas and resolved some of these problems, giving the theory more credibility. Still, Guth's role as the originator of the inflationary universe concept is undisputed. Guth's work didn't just explain existing puzzles, it also made bold predictions. The tiny fluctuations generated during inflation would eventually grow into galaxies, stars, and planets. Observations of the cosmic microwave background later confirmed the existence of these fluctuations, providing strong evidence for inflation. Beyond solving key cosmological problems, Guth's theory helped bridge the gap between quantum mechanics and general relativity. Inflation showed how quantum fluctuations on microscopic scales could have macroscopic effects, influencing the structure of the universe. This connection was a crucial step in advancing our understanding of how the universe operates on both large and small scales. Guth's inflationary model also introduced the idea that the universe we see is just a small part of a much larger structure. Inflation could be happening in other parts of space, creating new regions that we can never observe. This insight radically changed our view of the universe, suggesting that what we know might be just one piece of a much grander multiverse. Guth's contributions have made inflation one of the most widely accepted theories in cosmology. It fits with observations, solves long-standing problems, and continues to inspire new research into the nature of the universe. His work has fundamentally changed how we think about the origins and evolution of everything around us. Today, Guth remains an active figure in the field of cosmology, and his theory of inflation is still at the forefront of scientific exploration. While much remains to be understood about inflation and the early universe, Guth's work has laid a foundation that continues to shape modern cosmological theories. The inflationary universe is one of the most powerful ideas to emerge from modern physics, and Alan Guth's role in its development is pivotal. His insight that the universe underwent a period of rapid expansion has changed not only how we understand the cosmos, but also how we think about our place within it. String theory is one of the most ambitious and complex theories in modern physics. At its core, it suggests that the fundamental building blocks of the universe aren't particles, but tiny vibrating strings of energy. These strings are incredibly small, far smaller than anything we can currently observe, but their vibrations determine the properties of all matter and forces. What makes string theory so unique is that it attempts to unify all the forces of nature, including gravity, under a single framework. In traditional physics, gravity and quantum mechanics don't work well together, but string theory provides a way to bring these two worlds into harmony. This is why many physicists hope it could be the long-sought theory of everything. One of the central ideas in string theory is that the different particles we see, like electrons or photons, are just different vibrational modes of these fundamental strings. In other words, the type of particle is determined by how a string vibrates. Just like different vibrations of a guitar string produce different musical notes, different vibrations of these strings create different particles. String theory also requires the existence of extra dimensions beyond the familiar 3 dimensions of space and 1 of time. According to the theory, the universe actually has more dimensions, possibly 10 or even 11, although we can't perceive them because they're compactified or curled up in ways that are hidden from our everyday experience. These extra dimensions are crucial because they allow string theory to work mathematically. Without them, the equations don't hold up. This means that while these dimensions might be invisible to us, they play an essential role in the structure of the universe according to string theory. The inclusion of extra dimensions might sound strange, but it provides a potential explanation for some of the universe's most puzzling features. For example, the way gravity behaves might be a result of how it interacts with these hidden dimensions, which could help explain why it seems so much weaker than the other fundamental forces. One of the exciting aspects of string theory is that it not only includes particles that we already know, but it also predicts the existence of new particles. Some of these particles, like the hypothetical graviton, could explain forces like gravity at the quantum level. Discovering such a particle would be a major breakthrough for physics. String theory also introduces the concept of supersymmetry, which proposes that for every known particle, there is a corresponding partner particle. Supersymmetry could help solve several outstanding problems in particle physics, such as the nature of dark matter. However, none of these superparticles have been detected yet. Another important extension of string theory is M-theory, which suggests that strings are just one-dimensional slices of a more complex structure known as branes. These branes can exist in multiple dimensions and could provide new insights into the nature of the universe. M-theory attempts to bring together different versions of string theory into one unified picture. Despite its promise, string theory remains unproven. One of the major challenges is that its predictions are extremely difficult to test. The strings themselves are so small that current technology is nowhere near advanced enough to detect them, leaving string theory in the realm of mathematical speculation for now. String theory has sparked considerable debate within the scientific community. Some physicists believe it holds the key to unlocking the deepest mysteries of the universe, while others argue that without experimental evidence it's more philosophy than science. Nonetheless, the mathematical beauty and consistency of string theory continue to attract researchers. Even if string theory is never fully proven, it has already contributed to advances in other areas of physics. It has led to new ways of thinking about quantum mechanics, gravity, and black holes, and it continues to influence research in fields beyond particle physics. Its potential to reshape our understanding of reality is what keeps string theory at the forefront of theoretical physics. String theory suggests the existence of multiple universes through the idea of extra dimensions and the ways in which strings vibrate within them. Each different vibration pattern of a string could represent a different universe with its own unique set of physical laws. This opens the door to the possibility that countless universes exist, each governed by its own fundamental forces and particles. These extra dimensions that string theory relies on provide a natural framework for the multiverse. Since the extra dimensions can be compactified in various ways, different configurations of these dimensions could result in different universes. This means that depending on how these dimensions are folded or shaped, each universe could emerge with its own distinct characteristics. One of the most intriguing aspects of string theory is the idea of the landscape. This refers to the nearly infinite number of possible configurations that the extra dimensions could take. Each configuration would create a different vacuum state, essentially giving rise to a new universe. The landscape of string theory suggests that our universe is just one of many possible outcomes. M-theory, which is an extension of string theory, introduces the concept of higher dimensional objects called branes. According to M-theory, our universe could be a three-dimensional brane floating in a higher dimensional space. Other branes representing other universes could exist parallel to ours, possibly separated by just a tiny distance in these higher dimensions. These branes could collide or interact in certain ways, leading to the creation of new universes. Some physicists even suggest that the Big Bang might have been the result of such a collision between branes. If this is true, it would mean that universes are constantly being created in a vast multiverse. String theory also predicts the existence of multiple possible vacua or states of empty space. In each of these vacua, the properties of the universe, such as the strength of gravity or the behavior of particles, could be entirely different. This points to the existence of many different universes, each with its own vacuum state. The idea of cosmic inflation combined with string theory strengthens the case for a multiverse. During inflation, different regions of space could settle into different vacuum states, creating separate universes. String theory provides the mathematical tools to describe how these different vacua might arise, further supporting the multiverse concept. These multiple universes would not necessarily be accessible to each other. In fact, they could be completely isolated by the vastness of higher dimensional space or by the different physical laws that govern them. This makes it nearly impossible to detect these parallel universes directly, but string theory suggests they are mathematically consistent. Some interpretations of string theory propose that the constants of nature, like the speed of light or the charge of an electron, could vary from one universe to another. This variability would result in entirely different kinds of universes, some of which might not even allow the formation of stars or life as we know it. The existence of multiple universes also offers an explanation for why our universe seems so finely tuned for life. If there are countless universes with different physical laws, it's not surprising that one of them, by sheer chance, has the right conditions for life to develop. We just happen to live in that particular universe. String theory's multiverse concept has been met with both excitement and skepticism. On one hand, it offers a compelling solution to many problems in physics. On the other hand, it raises questions about how we can ever test or observe these other universes, since they exist outside the realm of direct observation. While experimental evidence for the string theory multiverse is lacking, the mathematical framework it provides continues to push the boundaries of our understanding. The idea of multiple universes is no longer just a speculative thought experiment, but a real possibility that stems from the deepest theories of modern physics. Extra dimensions play a crucial role in string theory, making the theory possible by providing the space for strings to vibrate in different ways. These additional dimensions, beyond the familiar three of space and one of time, are compactified, meaning they are curled up so tightly that they are invisible to us. Their existence allows strings to move and vibrate in ways that give rise to the particles and forces we observe. In string theory, the extra dimensions are not just a theoretical curiosity. They determine the properties of the universe. How these dimensions are shaped directly affects the vibrational modes of strings, and thus the physical laws that emerge in our universe. This means the structure of these extra dimensions could vary in other universes, creating entirely different realities. The idea of compactification is key to understanding how extra dimensions work. Although they are hidden from our everyday experience, they are still present at extremely small scales, smaller than we can currently observe. Their geometry influences everything from the strength of gravity to the behavior of particles. In some models, these extra dimensions could be as small as the Planck length, a tiny scale far beyond the reach of modern experiments. But their influence is vast, as the compactification of these dimensions determines the nature of our universe. In another universe, these dimensions could be shaped differently, resulting in different physical constants. Branes, or membranes, are another important concept linked to extra dimensions. In M-theory, branes are higher dimensional objects that exist within this extended space. Our universe could be a brane floating in a higher dimensional space, with other branes and possibly other universes existing parallel to ours. These extra dimensions might also explain why gravity seems so weak compared to other forces. One possibility is that gravity spreads out into these extra dimensions, diluting its strength in our three-dimensional space. This would account for why the gravitational force is much weaker than, say, electromagnetism. The way these extra dimensions are arranged could help solve long-standing problems in physics, like the hierarchy problem, which deals with the huge difference in strength between gravity and the other forces. By understanding how gravity behaves in these extra dimensions, string theorists hope to gain insight into why these forces behave so differently. Extra dimensions also play a role in the multiverse concept. Depending on how these dimensions are shaped, different universes could form with entirely different physical properties. Some of these dimensions might even allow for the existence of universes where the laws of physics are completely alien to what we know. In certain models, these extra dimensions could be large enough to have observable effects, but we haven't been able to detect them yet. For example, experiments are being conducted to search for signs of extra dimensions at high-energy particle colliders like the Large Hadron Collider. If extra dimensions are large enough, we might be able to observe them indirectly. Extra dimensions might also allow for the possibility of faster-than-light travel or shortcuts through space. Some theories suggest that by traveling through these higher dimensions, it could be possible to bypass the limitations of our three-dimensional space, creating a kind of cosmic shortcut or wormhole. Despite the fact that we can't directly observe them, these extra dimensions are an essential part of the mathematics that make string theory work. Without them, the equations wouldn't balance, and the theory wouldn't be able to describe the universe as we know it. Their existence is a cornerstone of string theory's framework. The role of extra dimensions in string theory is to expand our understanding of space and the universe itself. They offer new possibilities for how the universe operates and provide a way to unify the forces of nature. Even though we can't see them, these dimensions are integral to the underlying structure of reality. M-theory is an extension of string theory that brings together different versions of string theory into a single, unified framework. In M-theory, strings are not just one-dimensional objects, but can also exist as higher dimensional objects known as branes. These branes can have various dimensions, and they provide a more flexible model for describing the universe. One of the key implications of M-theory is the possibility that our universe is a three-dimensional brane existing in a higher dimensional space. In this view, other universes could exist as parallel branes, separated from ours by extra dimensions. These universes might have different laws of physics, making them entirely distinct from our own. M-theory also suggests that these branes can interact with each other. In some scenarios, collisions between branes could create new universes, much like how the Big Bang might have been the result of such a collision. This introduces the idea that the multiverse is dynamic, constantly evolving through interactions between branes. Another fascinating aspect of M-theory is that it includes the possibility of 11 dimensions. While we are only familiar with 4 dimensions in our everyday experience, these extra dimensions could house other universes. Each brane within this higher dimensional space could represent a different universe with its own unique properties. The addition of these extra dimensions provides a mathematical structure that allows for a nearly infinite number of possible universes. In this sense, M-theory supports the idea of a vast multiverse, where different universes are spread across different branes, each influenced by the geometry of higher dimensional space. One of the key features of M-theory is its ability to explain gravity in a new way. Gravity, according to M-theory, might not be confined to our universe, but could leak into other dimensions. This could help explain why gravity appears so much weaker compared to the other fundamental forces in our universe. The idea that gravity can interact with other dimensions also raises the possibility of communication or interaction between universes. If gravity can cross the boundaries between branes, it might be one of the few forces that connects different universes, although such interactions would likely be incredibly subtle and difficult to detect. M-theory also provides a potential solution to the problem of how the universe began. Instead of a single, unique event like the Big Bang, the birth of our universe could have been part of a much larger process involving brane collisions. This opens up the possibility that universes are constantly being created and destroyed within the multiverse. This theory also suggests that the constants of nature, such as the speed of light or the strength of gravity, might vary from one universe to another. Depending on the shape and size of the extra dimensions in each brane, the laws of physics could be different, leading to a diverse multiverse where each universe has its own unique characteristics. M-theory's ability to unite different forms of string theory has made it one of the most promising candidates for a theory of everything. By explaining both the fundamental particles and forces of our universe and the possibility of multiple universes, M-theory offers a way to bridge quantum mechanics and gravity in a way that no other theory has. While M-theory remains largely theoretical and is difficult to test experimentally, its mathematical consistency makes it a powerful tool for understanding the fundamental nature of reality. The multiverse it predicts is not just a collection of disconnected worlds, but a vast network of universes that exist within a single, higher dimensional framework. Ultimately, M-theory offers a new way of thinking about the cosmos, where the multiverse is not just a possibility, but a natural outcome of how the universe works on a fundamental level. It expands our understanding of what might lie beyond the observable universe and raises profound questions about the nature of existence itself. String theory, despite its elegance, faces several significant challenges and controversies. One of the most notable is the lack of experimental evidence. The scales at which string theory operates are so small, far smaller than any particle we can observe, that testing its predictions remains far beyond our current technological capabilities. Another major challenge is that string theory doesn't just predict one possible universe, but an enormous number of them. This vast landscape of solutions, potentially as large as 10 to 500, makes it difficult to know why our universe looks the way it does. Critics argue that this makes the theory too flexible, as it seems to allow for virtually any outcome. Some physicists also question whether string theory can be considered a scientific theory at all. Since many of its predictions are practically untestable, string theory runs the risk of being seen as more of a mathematical framework than a physical theory grounded in empirical data. For science to progress, there must be a way to test and potentially falsify a theory. One of the most controversial aspects of string theory is its reliance on extra dimensions. While these dimensions make the mathematics of the theory work, their existence remains speculative, as there's no direct evidence to support them. Without proof of extra dimensions, critics argue that string theory rests on an unproven assumption. The sheer complexity of string theory is another hurdle. Its equations are incredibly difficult to work with, and even after decades of study, many of its solutions remain unexplored or poorly understood. This complexity makes progress slow and raises the question of whether we will ever fully grasp all the implications of the theory. Another point of contention is the theory's compatibility with observable physics. While string theory promises to unify the forces of nature, it hasn't yet made a clear, testable prediction about the world we live in. Some physicists feel that a true theory of everything should provide more concrete insights into the known universe, which string theory has yet to deliver. There's also debate over whether string theory is the only path to unification. Alternatives like loop quantum gravity offer different approaches to merging quantum mechanics with gravity. Some researchers argue that focusing too much on string theory might limit exploration into other potentially viable theories. String theory's prediction of supersymmetry is also a controversial point. Supersymmetry proposes that every particle has a superpartner, but despite extensive searches, no superpartners have been found. This raises questions about whether string theory's assumptions about supersymmetry are correct. The theory's reliance on the concept of branes is intriguing but unproven. While branes help explain many aspects of string theory, they introduce additional layers of complexity that make it even harder to test. This leads to further skepticism about whether string theory can ever be experimentally verified. Some critics also argue that string theory is too detached from reality. They suggest that while the mathematics might be beautiful, it doesn't necessarily reflect the physical universe. In this view, string theory might be more of a mathematical curiosity than a real description of nature. The lack of a definitive string theory is another challenge. There are multiple versions of string theory, each with different strengths and weaknesses. M-theory was developed to unify these versions, but even that remains incomplete, leaving physicists with many open questions. Despite these challenges, string theory continues to attract interest because of its potential to explain deep mysteries about the universe. While the theory remains speculative, its ability to unify gravity with the other fundamental forces keeps it at the forefront of theoretical physics. Bubble universes are a concept that emerges from the theory of eternal inflation, suggesting that our universe is just one bubble in a vast multiverse. According to this idea, different regions of space experience inflation at different rates, with some areas slowing down and forming bubbles that each evolve into separate universes. These bubbles, including our own, are isolated from one another by the continuous expansion of space. Each bubble universe can have its own distinct properties, including different laws of physics. While our universe has certain physical constants, another bubble could have entirely different ones, resulting in a radically different reality. This variation in physical laws across bubbles helps explain the diversity that could exist in a multiverse. The separation between bubble universes is vast, often expanding faster than the speed of light. This rapid expansion prevents any direct interaction between bubbles, meaning each universe exists in isolation. Even though they are part of the same overall multiverse, the bubbles can never collide or share information. Bubble universes arise naturally from the idea of eternal inflation. While inflation in our universe ended billions of years ago, it continues indefinitely in other regions of space. As this inflation goes on, it constantly creates new bubbles, each forming a universe of its own. One fascinating implication of bubble universes is that the Big Bang might not have been a unique event. Instead of being the beginning of everything, the Big Bang could have been the result of a bubble forming in a larger multiverse. Other bubbles might have experienced their own versions of the Big Bang, giving birth to countless other universes. Although we live inside one of these bubbles, we can't observe other bubbles directly. The expansion of space between them is too great, and even if other universes exist just beyond our own, they remain forever out of reach. This makes it incredibly challenging to prove the existence of bubble universes. Still, some scientists believe that evidence of bubble collisions might be visible in the cosmic microwave background. If two bubbles ever brushed up against each other, it could leave an imprint on the radiation left over from the Big Bang. Detecting such a signal would offer a rare glimpse into another universe. The idea of bubble universes also raises the possibility that our universe might one day be destroyed by the expansion of another bubble. If a neighboring bubble were to collide with ours, the consequences could be catastrophic, potentially resetting the entire universe. However, this scenario remains purely speculative. Bubble universes also offer an intriguing explanation for why our universe seems so finely tuned for life. In an infinite multiverse, where each bubble has different physical properties, it's not surprising that one of these universes would have the right conditions for life to emerge. We just happen to live in that particular bubble. These bubbles can also exist in different dimensional structures. Some might have more than 3 spatial dimensions, while others could have fewer. This variation adds another layer of complexity to the multiverse and could lead to universes where the concept of space and time operates in ways beyond our understanding. The theory of bubble universes has been both praised and criticized for its speculative nature. On one hand, it offers a compelling framework for understanding the diversity of possible universes. On the other hand, without direct evidence, some argue that it remains more of a theoretical construct than a testable scientific theory. Regardless of whether bubble universes are ever proven, the concept continues to shape our thinking about the cosmos. It challenges the traditional view of the universe as a singular entity and opens up possibilities that extend far beyond what we can see or experience. In the context of the multiverse, bubbles form during a process known as eternal inflation. While inflation ends in certain regions, allowing those areas to evolve into universes like ours, it continues in other parts of space. In the regions where inflation stops, bubbles of space form, each growing into a separate universe. These bubbles form when quantum fluctuations cause pockets of space to slow down and exit the inflationary phase. Within these pockets, the rapid expansion halts, allowing matter to cool and coalesce, eventually leading to the formation of stars, galaxies, and other cosmic structures. Each bubble represents a new, self-contained universe. The process is driven by the energy field responsible for inflation, called the inflaton field. When the energy in this field decays in certain regions, it causes inflation to stop locally, and a bubble forms. As more and more regions experience this decay, new bubbles emerge, each becoming a distinct universe within the multiverse. In areas where inflation continues, space expands exponentially, pushing bubbles away from each other. This ensures that the universes remain isolated, with no possibility of interaction. Even though the bubbles may form close to each other initially, the inflationary expansion quickly separates them, creating vast distances between universes. The rate at which bubbles form is unpredictable, governed by quantum mechanics. Some regions of space may stop inflating and form bubbles rapidly, while others may continue expanding for an incredibly long time before forming new bubbles. This randomness means that the multiverse is constantly evolving, with new universes coming into existence over time. Once a bubble forms, it begins to expand and evolve, much like our own universe did after the Big Bang. Inside, the fundamental forces take shape, matter forms, and the universe cools and grows. While we can only observe our own bubble, string theory and eternal inflation suggest that countless others are undergoing similar processes. The boundaries between bubbles are defined by the expanding regions of space that separate them. These boundaries grow as inflation pushes the bubbles apart, preventing them from ever colliding. The space between the bubbles continues to stretch faster than the speed of light, making travel between universes impossible. Some theories suggest that the formation of a bubble is like the birth of an entirely new universe, complete with its own set of physical laws. Depending on how the inflaton field decays, each bubble could have different constants of nature, leading to a multiverse filled with universes that operate in radically different ways. Interestingly, the number of dimensions within each bubble could vary as well. While our universe has 3 spatial dimensions, another bubble could have more or fewer dimensions, resulting in a completely different structure for space and time. These differences could make some bubbles completely unrecognizable compared to our own universe. As the bubbles form, their interiors experience a period of rapid growth, similar to what we experienced during the Big Bang. This inflationary phase ensures that the universe inside the bubble becomes large enough to support the formation of galaxies and complex structures. Without this rapid initial expansion, a universe may not develop in a way that supports life. Despite the vastness of the multiverse, the bubbles remain forever disconnected. Even if they form relatively close to one another, the expansion of space ensures that they drift farther apart over time. This isolation is why we are unable to detect or observe other bubbles, even though they may exist just beyond the horizon of our own universe. The formation of bubbles is a continuous process in the multiverse. As long as inflation continues in some regions of space, new bubbles will keep forming, each giving rise to a unique universe. This ongoing creation of universes suggests that the multiverse is not static, but ever-growing, filled with an unending supply of new realities. Although bubble universes are thought to be separated by vast expanses of space, some theories suggest that interactions between them might still be possible. If two bubbles formed close enough together, there's a chance they could collide. Such a collision could leave observable effects, like distortions in the cosmic microwave background. These collisions would be incredibly rare given the rapid expansion that pushes bubble universes apart. However, if they did occur, the event could alter the structure of both universes, possibly merging them or dramatically changing their internal properties. This type of interaction might even create entirely new physical laws in the impacted regions. In some scenarios, the collision between bubble universes could cause shockwaves, affecting the formation of galaxies and other large-scale structures. This would leave an imprint on the universe's background radiation, offering a potential way to detect the presence of other universes. Scientists are still searching for signs of these imprints in the data. If bubble universes interact, it's possible that one universe might influence the development of another. For example, the energy from a nearby universe could seep into its neighbor, triggering new phases of inflation, or altering the rate of cosmic expansion. These interactions could change the course of evolution within a universe, creating unpredictable outcomes. One theory suggests that gravitational forces might be able to pass between bubble universes. If this is the case, we could potentially detect the gravitational influence of another universe, even if no other forms of communication or interaction are possible. This could provide indirect evidence of other bubbles in the multiverse. Another possibility is that the boundaries between bubbles are not entirely rigid. If the boundary between two universes weakened or fluctuated, matter or energy might briefly pass between them. While highly speculative, such an event could explain certain anomalies or phenomena in our universe that currently have no clear explanation. In some multiverse models, bubble universes might be stacked closely together in higher dimensional space. If this is true, interactions could occur through these extra dimensions, rather than through the three-dimensional space we experience. This opens up the possibility that the effects of other universes might be detectable in ways we don't yet understand. One particularly extreme possibility is that a collision between bubble universes could lead to the destruction of one or both universes. If the physical constants or laws of one universe overpower those of another, it could result in catastrophic changes to the fabric of space-time, possibly causing one universe to collapse or restart. There is also the idea that two bubble universes might never fully merge but could exchange information through quantum tunneling. This would allow for brief, fleeting connections between universes, through which particles or energy might pass before the bubbles drift apart again. It's a concept that remains purely hypothetical, but intriguing nonetheless. Even without direct collisions, the mere presence of other bubble universes could have subtle effects on our own. For instance, the gravitational pull of a nearby bubble might slightly influence the large-scale structure of our universe, bending light or altering the paths of galaxies. Detecting such small influences would be incredibly difficult, but not impossible. Despite the isolation of bubble universes due to the vast expansion of space between them, some models suggest that remnants of past interactions could still be observable. For example, certain irregularities in the distribution of matter or energy in our universe might hint at a distant collision in the early stages of cosmic inflation. Ultimately, while interactions between bubble universes are highly speculative, they provide an exciting avenue for exploring the multiverse. If such interactions can be proven or detected, they would revolutionize our understanding of not only the nature of the multiverse, but also the fundamental structure of reality itself. The idea of parallel universes remains largely theoretical, but some experiments have hinted at the possibility of their existence. Quantum mechanics, with its probabilistic nature, offers a starting point. The famous double-slit experiment, where particles behave like both waves and particles depending on observation, raises questions about how these different outcomes might coexist in separate universes. One area of research involves cosmic inflation. Inflation theory suggests that if our universe expanded rapidly after the Big Bang, other universes could have formed in the same process. While we can't observe these universes directly, scientists study the cosmic microwave background radiation for clues. Some hope that tiny anomalies in this background could indicate interactions with other universes. Another potential line of evidence comes from the search for gravitational waves. These ripples in spacetime, predicted by Einstein, have been detected, but researchers speculate that certain types of gravitational waves could signal the presence of another universe. If two universes ever collided, the impact might leave detectable waves. Quantum entanglement offers another curious phenomenon. When two particles become entangled, their states remain connected no matter how far apart they are. Some physicists wonder if this entanglement could extend across universes, suggesting that information might be shared between parallel worlds, though this remains speculative. Physicists have also looked at dark matter as a potential link to parallel universes. Dark matter is invisible and undetectable except through its gravitational effects, and it makes up most of the universe's mass. Some theories propose that dark matter might actually be matter from a parallel universe, interacting with ours only through gravity. There's also the theory of quantum tunneling. In this process, particles pass through barriers that seem impossible to cross, as if they momentarily exist in another realm before reappearing. While it's not direct evidence of parallel universes, quantum tunneling adds to the mystery of how particles can behave in ways that defy classical understanding. High-energy particle experiments, like those conducted at the Large Hadron Collider, are exploring conditions that might give insight into extra dimensions. Some physicists hope that these experiments will provide evidence of universes beyond our own, particularly if they reveal particles or forces that can only exist in higher dimensions. In some interpretations, black holes might offer a portal to parallel universes. The idea is that matter falling into a black hole could emerge in another universe, though no evidence currently supports this. Still, black holes remain one of the most promising places to look for clues about the multiverse. There's also the possibility of quantum computing offering indirect evidence of parallel universes. Quantum computers can process information at speeds far beyond classical computers, leading some to speculate that these devices might be tapping into parallel realities to perform calculations. Though this idea is still controversial, it's an intriguing area of study. Some researchers have suggested that ghost particles, or neutrinos, could offer a way to detect parallel universes. These nearly massless particles pass through ordinary matter almost undetected, but slight changes in their behavior might reveal the influence of other universes. Neutrino experiments are ongoing to better understand their nature. Another avenue comes from anomalies in the behavior of time itself. Some physicists speculate that strange time distortions, such as the unexplained acceleration of the universe's expansion, could be influenced by other realities. If time operates differently in parallel universes, it might explain these odd cosmic phenomena. Despite these fascinating theories, concrete evidence for parallel universes remains elusive. Many of the experiments and observations hint at the possibility, but fall short of providing definitive proof. The search continues, and as technology advances, we may eventually find more direct ways to test the multiverse hypothesis. Gravitational waves are ripples in spacetime, predicted by Einstein's theory of general relativity. They are produced by massive objects moving through space, like colliding black holes or neutron stars. The detection of these waves opened up a new way of observing the universe, offering insights into events that would otherwise be invisible. Some scientists believe gravitational waves could also provide clues about the existence of parallel universes. If our universe collided with another during its early stages, the impact could have left behind gravitational waves that we might detect today. These waves would be different from those caused by black holes, carrying information about that ancient collision. Researchers have started studying the cosmic microwave background for signs of such gravitational waves. Any irregularities in this background radiation could be evidence of our universe interacting with another through gravitational effects. This would be one of the most direct ways to observe the possible existence of a parallel universe. Another idea is that certain types of gravitational waves might pass between universes. If there are extra dimensions, as suggested by string theory, gravitational waves could travel through them, potentially allowing energy or information to move from one universe to another. This could explain some unexplained cosmic phenomena. One of the exciting prospects is that gravitational waves could reveal the structure of the multiverse itself. If the multiverse exists, gravitational waves might help us map out how different universes are arranged or even how they interact. Detecting such waves would transform our understanding of reality and our place within it. While current technology is limited, future advancements in gravitational wave detectors may help us explore these possibilities more deeply. As our ability to measure and analyze these waves improves, we may be able to detect faint signals that point to events outside our own universe, offering a glimpse into the multiverse. Some scientists speculate that the strength and patterns of certain gravitational waves could differ if they originate from interactions between universes. These differences would provide a distinct signature, helping us differentiate between waves from known astrophysical events and those from multiverse interactions. However, interpreting gravitational waves as evidence of parallel universes remains highly speculative. The waves we've detected so far have all come from black holes and neutron stars within our own universe. While the theory is intriguing, there's still a long way to go before we can confirm or disprove the multiverse connection through gravitational waves. Even so, the potential for gravitational waves to reveal hidden aspects of the universe keeps the idea alive. Every new detection brings us closer to understanding the full scope of what's possible. Gravitational waves are becoming one of the most important tools in the quest to understand both our universe and what might lie beyond. One challenge is distinguishing between the sources of these waves. Black hole mergers, supernovae, and other cosmic events all produce gravitational waves, and filtering out these signals to find something from another universe is a complex task. It requires careful analysis and new techniques in gravitational wave astronomy. The Laser Interferometer. Gravitational Wave Observatory, or LIGO, has already made groundbreaking discoveries by detecting these waves. As LIGO and similar observatories improve, there's hope that they may pick up more subtle and unusual gravitational waves, potentially offering clues about the multiverse. For now, gravitational waves remain one of the most exciting frontiers in the search for parallel universes. They may one day provide the first real evidence that our universe is just one part of a much larger multiverse, opening up new possibilities for exploration and discovery. The cosmic microwave background, or CMB, is the afterglow of the Big Bang, a faint radiation that fills the universe. It provides a snapshot of the universe when it was just 380,000 years old. By studying the CMB, scientists have been able to learn a great deal about the early universe and its structure. But there are anomalies in the CMB that some researchers believe could be hints of something beyond our universe. These small irregularities in temperature and density might be evidence of interactions with other universes or unknown forces acting on our own. One of the most famous anomalies is called the cold spot. It's a region in the CMB that's unusually cold, much colder than the surrounding areas. Some theories suggest that this could be the result of our universe colliding with another bubble universe, leaving behind a distinct mark on the CMB. Another possibility is that these anomalies are caused by the influence of extra dimensions. If extra dimensions exist, as predicted by string theory, they could distort the CMB in ways we can't yet fully explain. This could create patterns in the CMB that don't fit with current models of the universe. These anomalies are intriguing because they don't fit easily into the standard model of cosmology. While they might simply be statistical flukes or the result of processes we don't yet understand, they could also be the first signs of something much bigger, like the existence of other universes. Scientists continue to study these anomalies in the hopes of uncovering their true cause. The European Space Agency's Planck satellite provided detailed maps of the CMB, offering more precise measurements of these irregularities. However, even with this improved data, the anomalies remain unexplained. Some researchers are exploring whether these anomalies could be linked to dark matter or dark energy. These mysterious substances make up the majority of the universe's mass and energy, but their nature is still largely unknown. It's possible that the CMB anomalies are tied to these forces in ways we don't yet understand. Others suggest that the anomalies might be remnants of quantum fluctuations from the earliest moments of the universe's existence. If these fluctuations are connected to the formation of other universes, then the anomalies in the CMB could be indirect evidence of a multiverse. The idea that the CMB could hold the key to discovering parallel universes is both exciting and controversial. While some physicists are optimistic that these anomalies will lead to groundbreaking discoveries, others caution that the evidence is far from conclusive. Even if the anomalies aren't caused by other universes, they still present a mystery that challenges our understanding of the cosmos. Finding their origin could lead to new insights into the nature of the universe and the forces that shaped its evolution. Ongoing research and future missions will continue to refine our understanding of the CMB. As technology improves, we may be able to detect even smaller irregularities, potentially uncovering clues that have so far remained hidden. For now, the CMB anomalies remain one of the most tantalizing pieces of evidence in the search for parallel universes. Whether they point to another reality or reveal something entirely new about our own universe, they offer a glimpse into the deep, unresolved mysteries of the cosmos. Dark matter and dark energy play a significant role in shaping the universe, even though they remain some of the greatest mysteries in modern physics. Dark matter is invisible and doesn't emit or absorb light, yet we know it exists because of its gravitational effects on galaxies and clusters of galaxies. Without dark matter, the structures of the universe, like galaxies and stars, couldn't hold together. Dark energy, on the other hand, is even more mysterious. It's thought to be the force responsible for the accelerated expansion of the universe, pushing galaxies further apart at an increasing rate. While we can measure its effects on cosmic scales, we have little understanding of what dark energy actually is, or how it works. Both dark matter and dark energy could potentially offer clues about the existence of parallel universes. Some theories suggest that these unseen forces might be leaking from other universes into ours. This would explain why dark matter and dark energy interact with gravity, but are otherwise undetectable by our instruments. In the case of dark matter, one theory posits that it could be made up of particles from another universe that are only weakly interacting with ours. These particles might pass through our universe without interacting with normal matter, making them difficult to detect except through their gravitational influence. Dark energy, which drives the expansion of the universe, could also be connected to the multiverse. Some physicists speculate that the energy driving the expansion might come from other dimensions or universes. In this view, dark energy could be the result of forces acting beyond our observable universe, influencing it from the outside. The amount of dark energy in our universe seems to be finely tuned to allow galaxies, stars, and life to form. This precision has led some to suggest that our universe might be just one of many, each with different amounts of dark energy. In this multiverse scenario, we live in a universe with the right conditions for life simply because it happens to be one where dark energy is at the right level. Additionally, the study of dark matter distribution across the universe has revealed some anomalies, such as unexpected concentrations of dark matter in certain areas. These irregularities might hint at the influence of structures from other universes, bending space-time and affecting how dark matter behaves. Experiments aimed at detecting dark matter, like those using underground detectors or high-energy particle colliders, have so far been unsuccessful in directly observing these particles. However, if dark matter is interacting with our universe from another dimension or universe, it might explain why these experiments have not yet yielded results. Dark energy's impact on the future of the universe is also a subject of much debate. If the expansion driven by dark energy continues unchecked, it could eventually lead to a big rip, where galaxies, stars, and even atoms are torn apart. Alternatively, dark energy could fluctuate, leading to a different end for the universe or even spawning new universes. Understanding dark matter and dark energy is essential to solving some of the biggest questions in cosmology. If these forces are indeed connected to parallel universes, they could offer the first tangible evidence that the multiverse exists. Discovering how they work might unlock entirely new dimensions of reality. Theoretical models continue to explore how dark matter and dark energy fit into the framework of the multiverse. If these forces do originate from other universes, their study could lead to breakthroughs that fundamentally change our understanding of space, time, and the nature of existence. While we still have much to learn about dark matter and dark energy, Their mysterious presence suggests that the universe is far more complex than we currently understand. Whether they are linked to parallel universes or represent forces we have yet to comprehend, they are key to unlocking the secrets of the cosmos. Despite the intriguing theories, many physicists remain skeptical about the current evidence for parallel universes. One of the main criticisms is that much of the evidence is purely theoretical, relying on mathematical models rather than empirical data. Without direct observation, many argue that these ideas remain speculative. Another issue is the interpretation of cosmic microwave background anomalies. While some see these irregularities as potential signs of other universes, critics argue that they could be explained by more mundane factors. Small errors in data collection or previously unknown phenomena within our own universe might account for these anomalies. The multiverse hypothesis is also criticized for being unfalsifiable. If parallel universes exist but are completely disconnected from ours, then there may be no way to observe or interact with them. This makes it difficult to test the theory in a scientific way, leading some to argue that it falls outside the realm of observable science. Gravitational waves are another area where the evidence is inconclusive. While some researchers believe these waves could offer clues about the multiverse, the waves detected so far are well explained by black hole and neutron star collisions. No gravitational waves have been definitively linked to interactions with other universes. When it comes to dark matter and dark energy, their role in supporting the multiverse theory is often seen as speculative. While these forces remain mysterious, skeptics point out that we don't yet fully understand how they work within our own universe. It may be premature to connect them to parallel realities without clearer evidence. Some critics are concerned that focusing too much on the multiverse could distract from other important areas of research. By placing so much emphasis on theories that are currently untestable, scientists might be missing more practical explanations for the phenomena we observe. There's a fear that the multiverse might lead to intellectual stagnation if it cannot be explored directly. Additionally, the sheer number of possible universes predicted by multiverse theories presents a challenge. With such a vast range of potential realities, critics argue that the multiverse idea can be molded to fit almost any observation. This flexibility weakens its predictive power, making it harder to use as a scientific tool. Some physicists argue that the multiverse concept is philosophically appealing, but doesn't add much to our understanding of the universe. They question whether invoking countless parallel universes is necessary when simpler explanations might suffice. In their view, Occam's razor should be applied, favoring less complex solutions over the multiverse. The lack of evidence for supersymmetry also casts doubt on some multiverse models. Supersymmetry, a cornerstone of certain string theory frameworks, has not been observed in experiments like those conducted at the Large Hadron Collider. Without confirmation of supersymmetry, some of the theoretical support for the multiverse weakens. The idea that quantum mechanics implies a multiverse, as suggested by the many worlds interpretation, faces its own criticisms. Many physicists favor alternative interpretations of quantum mechanics that don't require the existence of parallel realities. For them, the multiverse is an unnecessary complication rather than a natural consequence of the theory. While the multiverse hypothesis may be mathematically consistent, its critics argue that science should ultimately be grounded in what can be observed and tested. Until new technologies or breakthroughs allow us to directly explore these ideas, the multiverse will remain a highly debated and speculative area of study. Despite these criticisms, the multiverse remains a compelling idea for many scientists. However, until more concrete evidence emerges, it will likely continue to be one of the most contested and speculative concepts in modern physics. Some scientists believe that the phenomena we attribute to parallel universes might be explained without invoking other realities. One alternative explanation lies within quantum mechanics, where the behavior of particles is often probabilistic. Rather than suggesting multiple universes, some physicists argue that quantum effects can be explained entirely within our own universe through superposition and uncertainty. The anomalies in the cosmic microwave background could also have explanations that don't involve other universes. These irregularities might be the result of unknown processes in the early universe that we haven't yet fully understood. Rather than pointing to a multiverse, they could simply reflect the complexities of cosmic evolution. Dark matter, which has puzzled scientists for decades, may not require the existence of parallel universes to explain its behavior. Instead, new theories of particle physics, such as the existence of a yet undiscovered particle, could account for the gravitational effects we observe without invoking other dimensions or realities. Another possibility is that the apparent acceleration of the universe's expansion, which is often linked to dark energy, could be due to a misunderstanding of gravity on a cosmic scale. Modified gravity theories suggest that we may not fully understand how gravity works over vast distances, potentially explaining cosmic expansion without needing to introduce parallel universes. The many worlds interpretation of quantum mechanics is often associated with parallel universes, but alternative interpretations like the Copenhagen interpretation or pilot wave theory offer explanations that don't involve multiple realities. These interpretations suggest that quantum phenomena can be fully explained within a single universe, without the need for branching timelines. Some researchers have proposed that black holes might not be gateways to other universes, but instead, regions of extreme space-time curvature within our own. If true, the strange behaviors observed near black holes might be fully contained within the framework of our universe, without suggesting the existence of other realms. String theory, often tied to the multiverse, has alternative interpretations that remain grounded in our universe. Some physicists believe that string theory's extra dimensions could be compactified in ways that don't lead to parallel universes, instead offering explanations for the forces and particles we observe without invoking a multiverse. The idea of cosmic inflation, which has been linked to the multiverse, could also have explanations entirely within our universe. Some models suggest that the early rapid expansion of space-time might not require the formation of separate bubble universes, but could instead be a phase of our universe's evolution that eventually stabilized into the cosmos we see today. There's also the possibility that our universe is simply one of many regions within a single vast universe. These regions might have different properties or physical laws, but they would still exist within one continuous space-time framework. This approach offers an alternative to the idea of isolated, independent, parallel universes. Another explanation for some of the observed cosmic phenomena might lie in the concept of higher dimensional space within our own universe. These extra dimensions could influence how matter and energy behave, offering insights into the mysteries of dark matter and dark energy without requiring multiple universes. Some phenomena attributed to the multiverse could be the result of unknown physics that we have yet to discover. As our understanding of quantum mechanics, relativity, and cosmology evolves, we may find that many of the questions leading to multiverse theories can be answered by new discoveries that fit entirely within our own universe. In the end, while parallel universes are a fascinating idea, there are many possible explanations for the mysteries of the universe that don't require them. As our knowledge grows, we may find that the answers to these cosmic questions are closer to home than we originally thought. The scientific community is divided on the topic of parallel universes, with some researchers deeply intrigued by the possibilities, and others more skeptical. On one side, supporters argue that the multiverse provides a natural extension of current theories in cosmology and quantum mechanics, offering solutions to long-standing puzzles about the nature of reality. Many proponents of the multiverse point to string theory and cosmic inflation as key frameworks that support the idea of multiple universes. They believe that the mathematical consistency of these models suggests that parallel universes are not just a theoretical possibility, but an inevitable consequence of how our universe operates. However, critics within the scientific community challenge the multiverse on the grounds of testability. They argue that without direct evidence, the multiverse hypothesis remains speculative. Science relies on observation and experimentation, and some physicists feel that the multiverse cannot be empirically tested with current technology. There's also concern about the philosophical implications of the multiverse. Some scientists feel that invoking an infinite number of universes to explain certain features of our own might be unnecessary or even counterproductive. They worry that the multiverse theory could divert attention away from more practical, testable theories. Supporters of the multiverse counter this by pointing out that the theory could still be indirectly tested. They argue that certain cosmic anomalies, such as gravitational waves or fluctuations in the cosmic microwave background, might provide evidence of interactions between universes. Although challenging to detect, these signals could validate the multiverse idea. Another point of debate involves the role of mathematics in the multiverse discussion. While some scientists are impressed by the mathematical elegance of theories like string theory and the many worlds interpretation, others feel that these theories are disconnected from observable reality. The reliance on complex mathematical models without direct evidence creates tension between different schools of thought. The lack of experimental evidence for supersymmetry, a key component of some multiverse theories, adds fuel to the debate. Some physicists had hoped that experiments at the Large Hadron Collider would reveal new particles supporting supersymmetry, but so far no such evidence has been found. This absence has led to questions about the validity of multiverse-related models. Despite the skepticism, the multiverse continues to captivate the imagination of many researchers. They believe that the multiverse could offer answers to questions about the fine-tuning of the universe, explaining why physical constants are perfectly aligned to allow life to exist. In their view, a multiverse makes the existence of life less improbable. Other scientists argue that the fine-tuning problem could be explained by mechanisms within our own universe, without the need for parallel realities. They suggest that new discoveries in particle physics or cosmology could eventually solve these puzzles, making the multiverse an unnecessary layer of complexity. The debate also touches on the nature of scientific progress. Some researchers feel that pursuing multiverse theories, even without direct evidence, pushes the boundaries of knowledge and could lead to breakthroughs in understanding. Others feel that focusing on testable theories within our own universe will yield more practical results. At the heart of the debate is a fundamental question about the nature of science. Should theories be considered valid if they cannot be tested or observed directly? This question fuels ongoing discussions in physics and cosmology, with no clear consensus in sight. In the end, the debate within the scientific community reflects the tension between exploration and evidence. While some see the multiverse as a bold new frontier, others remain cautious, preferring to focus on theories that can be directly verified through experimentation. This divide is likely to shape the future of cosmological research for years to come. The idea of parallel universes introduces intriguing questions for many religious beliefs. If multiple versions of reality exist, it could challenge traditional views of creation, particularly those that hold that God created one unique universe. Some might wonder how divine purpose applies across infinite realities, where every possible outcome is realized. In religions that emphasize moral accountability and judgment, parallel universes might complicate the idea of a singular afterlife. If multiple versions of each individual exist, leading different lives, it raises questions about which version of a person would be judged or how salvation could apply across all realities. For some, the existence of a multiverse might be seen as evidence of divine complexity. Rather than undermining religious belief, it could be interpreted as a reflection of a creator's infinite power, capable of sustaining not just one universe but many. This could expand the understanding of God's omnipotence in ways that are still consistent with faith. However, the notion of parallel universes might challenge beliefs in a single, linear path of history, as often presented in religious texts. If every decision branches into a new universe, it suggests that multiple versions of sacred events are unfolding across different realities. This could make it difficult to reconcile religious narratives with the idea of infinite alternatives. Some religious traditions, particularly those with a more mystical approach, might embrace the concept of parallel universes as part of a broader spiritual reality. In these views, alternate realities could be seen as different dimensions of existence, aligning with beliefs about spiritual realms that exist beyond the physical world. The concept of divine will might also be reinterpreted in a multiverse. If every possible outcome is realized, it raises questions about how divine intervention works across multiple realities. Does God guide events in all universes, or is there a specific focus on just one? These questions could prompt theological reflection on the nature of divine action. In religions that emphasize free will, the idea of parallel universes might both support and complicate those beliefs. On one hand, the existence of multiple realities where different choices play out could be seen as a testament to human freedom. On the other, it might raise questions about the significance of individual choices if every possible decision is made somewhere. The concept of a multiverse could also challenge traditional ideas of destiny or fate. If there are infinite paths, it suggests that no single destiny is fixed, which may conflict with religious teachings that emphasize a divine plan for each individual. This could lead to new interpretations of predestination and divine foresight. For some, the existence of parallel universes might inspire a broader, more inclusive view of spirituality. If the multiverse exists, it could suggest that reality is far more complex than previously understood, prompting people to explore spiritual ideas that accommodate this expanded vision of existence. This might foster a more open dialogue between science and religion. In certain religious traditions, the idea of a multiverse could be integrated into existing teachings about the nature of the soul. Some might propose that the soul transcends individual realities, experiencing different forms of existence across various universes. This could offer a new perspective on reincarnation or the afterlife, seen through the lens of parallel worlds. Others, however, might reject the idea of parallel universes altogether, seeing it as incompatible with their beliefs. For these individuals, the notion of multiple realities could undermine the idea of a single, purposeful creation, leading to a theological conflict between scientific theories and religious teachings. Ultimately, the concept of parallel universes poses deep questions for religious belief systems. Whether seen as a challenge or an opportunity for deeper reflection, the multiverse invites religious thinkers to reconsider how their faith applies in a reality that may be far more expansive than previously imagined. In a multiverse, the concept of morality could face significant challenges. If every possible decision creates a new universe where different outcomes are realized, it raises questions about the ethical weight of individual actions. The existence of infinite realities might dilute the sense of responsibility for any one choice. Some might argue that if every possible action is taken in some universe, the significance of moral decisions is lessened. After all, in another reality, you've already made the opposite choice. This could lead to a view that individual morality is less about the decisions themselves and more about the specific universe we happen to experience. However, others might contend that morality still holds strong in the context of the universe we live in. Even if multiple versions of ourselves make different choices in other realities, the ethical consequences of our actions still matter within the framework of the life we experience. This perspective keeps morality grounded in our personal reality. The multiverse could also complicate ideas of accountability. If there are infinite versions of each person making every possible decision, which version is morally responsible for their actions? This could lead to difficult questions about whether moral responsibility is spread across all universes or concentrated in the one we experience. The idea of infinite versions of ourselves making different choices might lead to moral relativism. If every action happens somewhere, some could argue that morality is simply a matter of perspective, varying from one universe to the next. This could weaken the idea of universal moral principles. On the other hand, some might view the multiverse as an opportunity to explore the full spectrum of moral possibilities. In this view, each universe serves as a test ground for different moral outcomes, offering a way to reflect on the consequences of choices that go beyond our own reality. This could deepen our understanding of ethical dilemmas. For those who believe in moral absolutes, the existence of multiple universes might pose a significant challenge. If different realities allow for all possible moral outcomes, it could raise questions about whether moral laws are fixed across all universes, or if they are subject to change in different contexts. Some might argue that the multiverse reinforces the importance of personal morality. In a world of infinite possibilities, the decisions we make in our universe could feel even more meaningful, as they define the specific reality we inhabit. This could lead to a stronger sense of moral purpose, knowing that we are shaping our own path in a sea of possibilities. The existence of a multiverse might also shift how we think about the consequences of our actions. If every possible outcome plays out somewhere, does this mean that the consequences of our actions are less significant? Or does it mean that we should focus more on the immediate impact of our choices in the universe we know? For some, the multiverse could provide an escape from moral guilt. If there is a version of ourselves in another universe making a morally perfect choice, does that ease the burden of our own mistakes? This could lead to a form of ethical disengagement, where individuals feel less responsibility for their actions in this universe. At the same time, the multiverse could inspire greater empathy. Knowing that there are infinite versions of ourselves making different decisions might lead to a broader understanding of the human experience. This could encourage more compassion for others, as each person is navigating their own moral path in a complex multiverse. In the end, morality in a multiverse would likely evolve in response to the knowledge that multiple realities exist. Whether it leads to greater moral relativism, personal responsibility, or new ethical frameworks. The concept of the multiverse invites us to rethink how we define right and wrong in an infinite landscape of choices and outcomes. Thought experiments have long been used to explore the implications of parallel universes. One famous example is Schrödinger's cat, a paradox that suggests a cat could be both alive and dead in a superposition of states. In the context of a multiverse, this paradox becomes less confusing, as each outcome would play out in a separate universe, with one where the cat survives and another where it does not. Another thought experiment is the idea of the quantum suicide scenario, where a person could theoretically survive in some branches of the multiverse, even after repeated life-threatening events. In each case, a universe continues to exist where the person survives, raising philosophical questions about the nature of death and continuity in a multiverse. The ship of Theseus problem, which asks whether an object remains the same after all its components have been replaced, takes on new dimensions in a multiverse. If there are countless versions of the ship across different universes, each one slightly different, it challenges our understanding of identity and persistence over time. A similar question arises when we think about personal identity. If multiple versions of ourselves exist in parallel universes, each making different choices, which version is the real you? This brings up deep philosophical questions about what defines individuality and whether any single version of a person can be considered the true self. The trolley problem, a classic ethical thought experiment, also gains new complexity in a multiverse. If each possible action creates a new universe, where one outcome involves saving lives and another results in death, what moral weight do our decisions carry? Does it change how we approach ethical dilemmas if every outcome occurs in some universe? Another interesting question is whether knowledge or truth changes in a multiverse. If different universes have different physical laws, what counts as objective truth? This raises questions about whether knowledge is universal or if it changes depending on the universe in which it is observed. Philosophers also wonder about the nature of time in a multiverse. If each universe follows its own timeline, what does that mean for our understanding of cause and effect? Can events in one universe influence another, or are they entirely isolated? These questions challenge our traditional views of temporal order. Another thought experiment considers the role of determinism. If every possible decision leads to a branching universe, does this mean everything is determined in advance? Or does free will still have meaning within each individual universe, even if every other choice is playing out somewhere else? The existence of parallel universes also prompts questions about probability. In a multiverse where every possibility is realized, does probability still have significance? If everything happens somewhere, then unlikely events might be common in some universes, making us rethink the nature of chance and randomness. Philosophers have also debated whether the multiverse implies the existence of multiple forms of consciousness. If every version of you exists in different realities, are all those versions conscious in the same way? Or does consciousness depend on the particular path you experience in your own universe? The concept of morality is also explored in thought experiments involving the multiverse. If every moral choice leads to a universe where the opposite decision is made, does that mean morality is relative to the universe? Or is there still an overarching ethical framework that applies across all realities? Finally, the multiverse raises questions about the ultimate meaning of life. If infinite versions of reality exist, each with different outcomes and possibilities, does this expand or diminish the significance of any one life? Thought experiments like these challenge us to reconsider what it means to live with purpose in a potentially infinite multiverse. Simulation theory suggests that our reality might be an artificial construct, created and controlled by an advanced civilization. In this scenario, everything we perceive as real, is actually a simulated environment, running on a highly sophisticated computational system. The theory raises the possibility that we are essentially living inside a giant computer program. One of the key parallels between simulation theory and the idea of parallel universes is the concept of multiple realities. Just as parallel universes suggest that there could be countless versions of reality, simulation theory implies that there could be many different simulations, each with its own rules and characteristics. These simulated worlds could exist side by side, similar to how multiverses are imagined. Another connection lies in the question of free will. If we are living in a simulation, our choices might be pre-programmed or influenced by the rules of the simulation. This idea echoes the philosophical questions raised by the multiverse, where free will is complicated by the existence of multiple versions of ourselves making every possible decision. Simulation theory also mirrors the multiverse in how it challenges our understanding of identity. If we are simulated beings, are we truly real? This parallels the question of personal identity in a multiverse, where multiple versions of a person exist, raising doubts about what constitutes the true self. The possibility of external creators or programmers in simulation theory can be seen as similar to the idea of higher dimensional beings or forces influencing parallel universes. Just as a multiverse might be shaped by unknown physical laws or dimensions, a simulated universe could be controlled by entities existing outside our understanding of reality. Both simulation theory and multiverse theories explore the limitations of human perception. In a simulation, the boundaries of what we can observe and experience are determined by the simulation itself. Similarly, in a multiverse, we might only be able to perceive our own universe, while others remain hidden from view. Some proponents of simulation theory point to technological advances as potential evidence. As our ability to create virtual worlds improves, it becomes easier to imagine that a far more advanced civilization could simulate entire universes. This notion has parallels with the multiverse, where the existence of multiple realities might seem plausible due to the sheer scale of the cosmos. In both theories, there's an underlying question about the nature of reality itself. Simulation theory suggests that what we experience as real might be nothing more than data, while the multiverse suggests that reality is far more expansive than we can observe. Both ideas push the boundaries of what we understand about existence. The idea of glitches or inconsistencies in the simulation also has parallels with the anomalies sometimes attributed to the multiverse. Just as simulation theory speculates that unexplained phenomena could be errors in the program, multiverse theories suggest that cosmic anomalies could result from interactions between different universes. Both simulation theory and the multiverse invite speculation about the ultimate fate of reality. In a simulated world, the simulation could theoretically be turned off at any time, ending existence as we know it. Similarly, in a multiverse, universes might collide, collapse, or evolve in ways that bring about their end. Both theories challenge the idea of a singular objective reality. In simulation theory, the reality we experience might be just one of many possible simulations. In the multiverse, our universe is one among countless others, each with its own version of events and physical laws. This leads to deep philosophical questions about what reality truly is. Ultimately, both simulation theory and the idea of parallel universes force us to confront the possibility that our understanding of existence is limited. Whether we are part of a simulated world or just one universe in an endless multiverse, these theories push the boundaries of what we think is possible, leaving us to question the nature of everything we know. Many scientists prefer simpler explanations because of a principle known as Occam's razor. This principle suggests that when presented with competing hypotheses, the one with the fewest assumptions is often the best choice. Simpler explanations are generally easier to test and verify, making them more practical for scientific inquiry. Some scientists argue that complex theories like the multiverse introduce too many variables without providing direct evidence. They believe that focusing on simpler models, which rely on known forces and observations, can lead to more concrete progress in understanding the universe. Complexity, they suggest, may obscure more straightforward solutions. Simplicity also tends to align with testability. The more assumptions or variables a theory includes, the harder it becomes to design experiments that can confirm or disprove it. For many researchers, A theory that can be tested and falsified is far more valuable than one that cannot be directly observed or measured. There's also a preference for simplicity because of the track record of successful scientific theories. Many of the most groundbreaking discoveries, from Newton's laws of motion to Einstein's theory of relativity, are elegant in their simplicity. These theories rely on fundamental principles that explain a wide range of phenomena without unnecessary complications. Some scientists are skeptical of theories like the multiverse because they feel that these ideas go beyond what is necessary to explain the data we observe. They argue that we should first exhaust all simpler explanations before entertaining more speculative theories. For them, complexity should only be introduced when absolutely required to solve a problem. Additionally, simpler theories often have greater predictive power. A theory that relies on fewer assumptions can more easily be applied to predict new phenomena or make accurate forecasts about how the universe behaves. Complex theories, by contrast, may be more prone to error because of their reliance on multiple interacting factors. Simplicity can also make a theory more broadly applicable. A model that explains many different aspects of the universe with a few basic principles is highly valued. Scientists often seek universal laws that apply across various contexts, and simpler theories tend to achieve this goal more effectively than complex, specialized ones. There's also a practical reason for preferring simpler explanations. They are often easier to communicate and teach. A theory that can be easily understood and shared with the scientific community, and even with the public, tends to gain wider acceptance. Complex theories can create barriers to understanding, even among experts. In fields like cosmology, where many questions remain unanswered, simpler theories provide a clearer path forward. They allow researchers to build on a solid foundation of existing knowledge, testing one idea at a time. Complex theories can sometimes feel overwhelming, especially when they lack direct evidence or testability. Some researchers argue that simpler explanations are more likely to reflect the true nature of the universe. They believe that the fundamental laws of physics should be elegant and concise, rather than convoluted. For these scientists, the beauty of simplicity is a guiding principle in the search for truth. While simpler explanations are not always correct, they provide a more manageable starting point for scientific investigation. Many researchers prefer to build from what is known and established, only expanding into more complex theories when absolutely necessary. This incremental approach has proven successful throughout the history of science. Ultimately, the preference for simpler explanations reflects a desire for clarity, precision, and testability in scientific theories. For many scientists, simplicity is not just a matter of convenience, but a philosophical commitment to understanding the universe in its most fundamental form. Throughout this video, we've explored the fascinating concept of parallel universes and the many theories surrounding them. From the origins of the multiverse idea in cosmology and quantum mechanics, to the philosophical and ethical implications, we've seen how this idea challenges our understanding of reality. Whether it's the scientific frameworks that support it, or the philosophical questions it raises, the multiverse remains a topic of endless curiosity and debate. We began by discussing the foundations of the multiverse, including inflationary theory and quantum mechanics, which both provide possible avenues for the existence of parallel realities. These theories, while compelling, are still largely speculative and face challenges in terms of direct observational evidence. Next, we delved into the key scientific figures behind these ideas, such as Hugh Everett and Alan Guth, whose groundbreaking work has shaped much of what we know about the multiverse today. We also explored how the multiverse fits into current physics models, including string theory and the concept of cosmic inflation. We then shifted to more theoretical frameworks, such as loop quantum gravity and holographic universe theories, which offer alternative explanations for the nature of space-time. Each of these theories presents unique approaches to understanding how our universe might be connected to others, or whether the concept of parallel universes is even necessary. Philosophical questions also play a crucial role in the multiverse debate. We explored what the existence of parallel universes might mean for free will, morality, and personal identity. If every possible decision creates a new universe, it raises profound questions about the significance of our choices and the nature of human consciousness. We also touched on how simulation theory parallels the multiverse concept, suggesting that, what we perceive as reality could be an artificial construct. This idea, along with the multiverse, challenges the very fabric of our understanding of existence, pushing us to rethink what is real and what might simply be beyond our perception. Moreover, we looked at the scientific community's divided stance on these ideas, with some preferring simpler explanations that don't require the assumption of multiple universes. The debate between complexity and simplicity continues to drive research, shaping the way we approach these unresolved questions in cosmology and physics. We explored alternative explanations within our own universe, considering whether dark matter, dark energy, and other cosmic phenomena might be explained without the need for parallel realities. These ideas offer simpler solutions but still leave room for further exploration and discovery. In the end, while we don't have all the answers yet, the concept of parallel universes offers an exciting frontier for both science and philosophy. Whether it's through modified gravity theories, loop quantum gravity, or entirely new frameworks, the quest to understand the multiverse pushes the boundaries of human knowledge and imagination. If you enjoyed this deep dive into the mysteries of the universe, don't forget to like this video and subscribe to our channel. There's plenty more to explore on these topics and beyond, so check out the rest of our videos and stay tuned for more fascinating discussions. Thanks for watching, and we'll see you in the next one.